Now we're going to look at units 5 and 6 on rational expressions and radical expressions. So we're going to start with simplifying, multiplying, and dividing rational expressions. And when we're doing that, that's where we just factor all the things and see what cancels. So this first problem, we can factor what multiplies to 2 and adds to -3 would be -2 and -1. So w minus 2 times w minus 1 over, back to the bottom, what multiplies to 3 and adds to 4, which is 3 and 1. So w plus 3, w plus 1. And I'm just going to copy down what else I had. Remember, when we are multiplying fractions, whether they have these or just numbers, we're multiplying across the top and across the bottom. So we can cancel as long as a factor is in the top and the bottom. So I can cancel a w minus 1 and a w plus 1. So my final answer for this would be w minus 2 over w plus 3. When we're dividing, it's the same idea as multiplying, except for we have to keep the original, the first fraction, change your division to multiplication, and flip your fraction. We're multiplying by the reciprocal. And now we proceed like the first problem and factor. This one, all I need to factor is the right fraction. So k plus 3, k minus 3. In the denominator, I have a GCF of 2. So 2 times k plus 3. I'm going to put parentheses around that first fraction's denominator so it's easier to see what's going on. And then I have a k plus 3 in the top and bottom, a k minus 3 in the top and bottom. So I'm left with 2 over 2, which just reduces to 1. When we're adding and subtracting, we have to have a common denominator. In order to find a common denominator, the first thing I have to do is factor. So let's factor these denominators. I get a plus 3, a minus 3, and then what multiplies to 9 and adds to 6? 3 and 3. So a plus 3, a plus 3. Now I need to compare. So I have 1 a plus 3, 2 a plus 3s. A minus 3, the other one doesn't have a minus 3, so I need to multiply by a minus 3. And then I have another a plus 3 in this right fraction. So just because the first fraction had an a plus 3, it didn't have 2 of them, so I do need to multiply by that again. So my numerator is going to simplify. I'm just going to do that and not write my denominator for a second. 3 times a plus 3 plus 2 times a minus 3. So we're going to distribute and combine like terms. So I get a plus 3 over my big fat denominator, which was a plus 3, a minus 3, a plus 3. But since we have an a plus 3 in the top and the bottom, this whole thing will simplify to 1 over a minus 3, a plus 3. Same thing when you have a common denominator, so let's factor the bottom of the right fraction, p plus 1, p minus 1. So they both obviously have a p minus 1, and I need to multiply the first fraction by p plus 1. So my numerator is 2p times p plus 1 minus 4, so 2p squared plus 2p minus 4. And this actually looks like it might factor, so I'm going to check with factoring in a second. So let's see. I have a GCF. So 2 parentheses p squared plus p minus 2. And we do have something that multiplies to -2 and adds to 1. That's 2 and -1. So we have 2 p plus 2 p minus 1 over p plus 1 p minus 1. And we do have a factor that's going to cancel. So we do always want to check, not necessarily always going to have something to cancel, but it's good to check. Now we're going to look at your favorite thing in the world, which was rational function graphs. So I'm going to try something different, and we're going to go through and find these different components in each equation at a time versus going through one problem at a time. So first we're going to look at horizontal asymptotes. Horizontal asymptotes have to do with the degree, or the highest exponent in the top and the highest exponent in the bottom. So when I have exponents in the top and bottom that are the same, then my horizontal asymptote is y equals their coefficient. So y equals 3 over 1, which would just be 3. In the second problem, the degree of the top is 1 and the degree of the bottom is 2. When the degree of the numerator is less than the denominator, my horizontal asymptote is y equals 0. So if I look at problem 3, I have the same thing going on. I have x to the first over x squared, so my horizontal asymptote is y equals 0. The last one, I have the same thing. If instead, here's just like some other random example, if I had 4x squared over x minus 2, there would be no horizontal asymptote. Okay. Next, let's look at the y-intercepts. Y-intercepts have to do with when I substitute in 0 for x. In this first fraction, when I substitute 0 in for x, I get 0 over 0 minus 16, which is negative 16, which reduces to 0, 0. If I plug in 0 to the next one, I get 4 over negative 9. 0 to the next one, I get negative 12 over 6, so that reduces to 0, negative 2. And then we end up with something weird. When I plug in 0, I get 0 over 0, which is undefined, so I have no y-intercept on that last problem. Okay. Now on all of these, we're going to go through and factor. So the first one, I have 3x squared over x plus 4, x minus 4. Then I have 2 times x plus 2 over x plus 3, x minus 3. Six times x minus 2 over x minus 2, x minus 3. And 4x over x times x minus 2. All right, so let's look for holes. Holes mean that we have the same factor in the top and the bottom. So this first one, I don't have a hole. No hole. The next one, no hole. If we go to the bottom row, I do have some holes. So I notice that I have the same factor, x minus 2, x minus 2. That means that my hole has an x value of 2, because 2 minus 2 is going to make that factor 0. Once I've identified my x value, I cross out that factor, and I plug in 2 to my equation that I have left. So 6 over 2 minus 3. Two minus 3. So 2 minus 3 is negative 1, and 6 divided by negative 1 would be negative 6. So 2, negative 6. This last one is your favorite problem. I put like a giant star or something next to it, because that is what we're really messing up on, is this exact question, which is when you have a hole that is a factor of x. So when I have x and I need x to be equal to 0, all that makes x 0 is 0. Then I cross off that whole, so I reduce to 4 over x minus 2, and when I substitute 0 into that, I get 4 over negative 2, which would give me 0, negative 2. All right. I'm going to do x-intercepts and vertical asymptotes together. So x-intercepts are when the top of my fraction is equal to 0. So what would make 3x squared equal to 0? Well, if x was 0. What would make the denominator equal to 0? If x was equal to negative 4 or x was equal to positive 4. Doing the same thing on the right, what would make the top equal to 0? Negative 2. And what would make the bottom equal to 0? X equals negative 3 and x equals positive 3. Looking at my more special situations on the bottom, what is going to make the top of this fraction equal to 0? Nothing, because nothing is ever going to make 6 equal to 0. And what makes the bottom equal to 0? Just x equals 3. If I have 4 equal to 0, 4 can't equal to 0, so there's no x-intercept. And my vertical asymptote is the bottom set equal to 0, so x equals 2. Overall, we're doing well with rewriting and simplifying our radicals. So what you need to remember for this is that x is to the power over root. Roots go in the ground. So my base in the first problem is x, my power is 5, and my root is 4. When I have a negative exponent, that means it needs to go in the denominator. So 1 over x, power is 3, root is 5. My first step to simplify numbers is to change it to the radical form we just did. So 25 to the negative 3/2 would be 1 over the square root of 25 cubed. And when we simplify, we want to do the root first. So this is 1 over the square root of 25, so that'd be 5. And then I'm going to cube that, and I get 1 over 125. Change 49 to the 3/2 to a radical form. Square root of 49 cubed. The square root of 49 is 7, and 7 cubed is 343. When we're simplifying variables, you want to do the number, the coefficient, just like normal. So if I'm doing the cube root of 108, I'm going to do a factor tree. So maybe I know that's even, so let's do 2 and 54. And then I'm looking for perfect cubes, so I see that this is 27 times 2. And then we can keep going down, or like when we talked about looking for perfect cubes and perfect squares, I know that I'm going to be doing the cube root of 27, so I'm going to shortcut this a little bit and use my powers of observation to know that this will be 3 cube root of 4. Okay, I'm just doing that. 2 times 2 is giving me the 4 over here, and then the cube root of 27 is 3, and that gets to go outside. Now let's look at our variables. So we're going to do 16 divided by 3. 16 divided by 3. 3 goes in 5 times, so I get to take out an a to the 5th, and that has a remainder of 1, so underneath I have a to the 1st. Then we're going to go b to the 9th. 9 is divisible by 3 times, so I get b cubed, and that obviously has a remainder of 0, so I don't have anything else left under my radical. Make sure you don't forget to put your cube root next to your radical. Okay, square root of 48. So let's try our perfect square method. 48 is 16 times 3. So number-wise, this is going to simplify to 4 square root 3. Leave yourself some room. Now I'm going to do a squared. So 2 divided by 2, because we're doing a square root, goes in once. So a to the first. B, we're doing cubes, so 3 divided by 2 goes in once. So b to the first with a remainder of 1b. And then c to the fourth, 4 divided by 2 goes in twice. Sometimes these problems are harder to know exactly how someone wants to do your answer. So that's where, if it's a multiple choice question, you look at what your answers are. So I noticed that my answers, my numbers have been simplified, and my exponents are fractions. So what is the cube root of 25? That's going to be 5. And then x, my power is 4, and my root is 3. So that's going to be answer choice B. Next up, we have our rational exponents that follow the same rules as normal exponents, and then we're just going to use our calculator to simplify things. So what we need for these are, remember, mad, seam. When you multiply the same base, you add the exponents. When you divide the same base, you subtract the exponents, and when you raise an exponent to an exponent, you multiply the exponents. So in the first problem, I have exponents being raised to other exponents. So that means I'm going to do exponent to exponent. I'm going to multiply. So I'm going to do a to the 1/3 times 12, b to the 3/4 times 12. So 1/3 of 12 is going to give me 4. And then 3 times 12 is 36, divided by 4 is 9, so b to the 9th. When I have coefficients, like in part B, you just do the operation. So 4 times 6 is going to be 24. And I'm going to go ahead, even though I have these negative exponents, I'm going to go ahead and add them together because I'm multiplying the same base, so I add the exponents. So x to the negative 2/3 plus negative 1/6. So that would be negative 5/6. 24x to the negative 5/6. And negative exponents are like negative people. They're not happy where they are. So that x is going to go down to the bottom. Okie dokie. That is an exponent, even though I wrote it really large. All right, now we are dividing the same base, so we're going to subtract the exponents. So this is going to be x to the 3/5 minus 2/3. And y'all have a calculator you can do, so I have 9 minus 10 over 15. So I get x to the negative 1 over 15. Negative exponents are not happy, so it's 1 over x to the 1/15. Now we have 1. It's a little more complicated, so we have a lot of different ways we could do this. I noticed that it's division for all of these variables, so the one way you could do this is to go ahead and just subtract the exponents for each of these, and that works totally fine. Just when you have a negative exponent, it means it moves to the denominator. I like to, though, get rid of any negative exponents, so I'm going to move any negative exponents I see to the other spot in the fraction. So that means a to the negative 1/3 is going to move up, then b to the negative 2 is going to move up, and c is going to move down. So I'm just going to do all that. A to the 1/3, a to the 2/3, b squared, and then c to the 3/4, c to the 7/4. Okay, now when I look at these, each of my variables is being multiplied to the same base. So that means I'm going to add each of these exponents. So a to the 1/3 plus 2/3 is just going to be a to the 3/3, which is a. b to the first times b squared is going to be b cubed over 3/4 plus 7/4 is 10/4, which will reduce to 5/2. The next problem, we have an exponent to an exponent, and when we have an exponent to an exponent, we multiply the exponent. So I get x to the, when that reduces, it will be 3/2. We have another one where we're going to be simplifying. So the 4th root of 81, if you have memorized, is going to be 3. But say I don't have it memorized, that means I get to do my favorite factor tree. 81 is 9 times 9. 3, 3, 3, 3. So I have one group of 3. And then if I do 4 divided by 4, I just get 1. So 3x. That simplified pretty quickly. All right, our last couple problems are on simplifying when I have radicals, and we're just going to focus on square roots. So when I'm adding and subtracting, I have to have the same radicand. That's the number underneath the radical, which right now doesn't look like I have anything that's the same, but I need to simplify. So I can simplify both square root of 28 and square root of 63. So I'm going to first do that. And once again, the more you can do perfect squares for this, it will really make your life a lot happier, but you'll get the same answer if you don't and you still factor tree these puppies. I'm just giving you life advice. Take it or leave it. So the biggest perfect square that goes into 28 is 4. And that's 4 times 7, so that would give me 2 square root of 7. Biggest perfect square that goes into 63 is 9. So that would be square root of 9 is 3. And I'm left with square root of 7. So I'm already seeing, hey, maybe I'm going to have a whole bunch of stuff to combine. So I'm going to simplify my coefficients first. 6 square root 7 minus 4 square root 7 plus 6 square root 7. So 6 minus 4 is 2, plus 6 is 8, square roots of 7. The next one, we need to be careful not to kill any puppies. We want to rewrite this quantity squared, remember, means 3 root 2 plus 2 times itself, 3 root 2 plus 2. So I'm going to multiply that using the box, but if you want to do that other thing I don't talk about, then you can as well. All right. If you can do these in fewer steps, then that's fine, but I'm going to show all my work. So when we multiply radicals, you multiply what's outside, so that would be 9, and you multiply what's inside, which would be square root of 2 times 2 is 4. Then we get 6 square root 2, 6 square root 2, and 4. So 9 square root 4, I can combine my 6 square root 2's, so 12 root 2 plus 4. Square root of 4 is obviously 2, so that part is 18, and 18 plus 4 is 22. I have another multiplication problem, so I'm just going to use my box again. Whoop. 8 times 7 is 56. Negative 8 root 2, 7 root 2, and then negative square root of 4, which is just going to be minus 2. So I get 54 minus square root of 2. And the last one is I need to rationalize the denominator. That means I need to multiply by the conjugate. The conjugate is when I change the sign in between my two numbers. So 1 minus the square root of 2, 1 minus the square root of 2. I'm going to multiply the bottom using the box, but you could shortcut it if you know how to do that. That's fine. 1 times 1 is 1, negative square root of 2, positive square root of 2, those cancel. That's the whole point of rationalizing. Minus square root of 4, and the square root of 4 is just 2. So 1 minus 2 is what's in the denominator, so that's just -1. And then I get square root of 2, distribute, minus square root of 4. So square root of 2 minus 2, all over -1. And those are pretty easy to simplify, so I'm going to divide both of those by -1.